Close your eyes for a second. Feel that, the warmth on your skin, the light behind your eyelids, that's sunlight. And it's impossible. I'm not being dramatic. I mean, it's literally impossible. According to the laws of physics, the same laws that built your phone, your car, the bridges you drive over, the sun shouldn't be shining. It should be a cold, dead ball of gas. You shouldn't be here. I shouldn't be here. None of this should exist, but here we are. So what's going on? Why does the sun shine when the math says it can't? The answer's going to sound insane, like I made it up, but I didn't. Nature did. And once you see it, you'll never look at sunlight the same way. Let's go. Before we talk about the sun, I need you to do something right now. Push your palms together, hard. Feel that resistance. That solid wall between your hands. That's a lie. You think your hands are solid. They feel solid. But here's what they actually are. Empty space. Almost entirely empty space. If you zoomed into an atom, really zoomed in, you'd find it's like a football stadium with a marble at the center. That marble, the nucleus, the electrons. They're like gnats buzzing around in the nosebleed seats. Everything else, nothing. Vacuum. So when you press your hands together, you're really just pushing emptiness against emptiness. Two clouds of nothing trying to pass through each other. And theoretically they should, but they don't. Why? Electricity. The electrons in your left hand negatively charged. The ones in your right hand also negatively charged. And there's one rule in this universe you can bet your life on. Like charges hate each other, they repel with a force so violent, so overwhelming that what you feel as solid is actually just electrical hatred. And here's the kicker. This force is staggeringly strong. Stronger than gravity by a factor you can't even imagine. If you and a friend stood arm's length apart, and each of you had just 1% more electrons than protons, just 1%, the repulsive force between you would be strong enough to lift the entire planet Earth. That's not a metaphor. That's the math. Now hold that thought, because this force is about to become a huge problem. Let's go to the sun. Deep in the core, it's chaos, stripped hydrogen nuclei, protons, bouncing around, colliding, jostling in this hellish soup. The temperature, about 15 million degrees Celsius. Sounds hot, right? It is hot, hotter than anything you'll ever touch. But here's the thing. In the world of nuclear physics, 15 million degrees is freezing colder, because to make the sunshine you need fusion. You need to take two protons and smash them together so hard they stick. Once they touch, the strong nuclear force, nature's superglue, snaps them together and releases energy. That energy becomes light. That light becomes life. But there's a problem. Those protons are both positively charged. And just like your hands, they repel. But unlike your hands, these guys are tiny. To fuse, they have to get close, really close, closer than the electrical force wants to allow. Imagine two cars racing toward each other, but both have powerful magnets on their bumpers, north poles facing out. As they approach, the magnets push back. If they're not moving fast enough, they slow down, stop, and bounce away. No collision, no fusion, no light. So we measure how fast the protons in the sun are moving. We calculate their kinetic energy based on that 15 million degree temperature. And we find something horrifying. They're too slow. On average, a proton in the sun doesn't have nearly enough energy to break through that electrical barrier. It's like trying to roll a bowling ball up a mountain. It gets partway up, loses steam, and rolls back down every time. According to classical physics, the physics of Newton, of Maxwell, of every bridge and rocket we've ever built, the probability of two protons touching in the sun is essentially a zero. The sun should be dark, but look outside, it's not. So, what's happening? Here's where things get weird. To understand why the sun shines, you have to stop thinking about protons as little billiard balls. You have to let go of the idea that things are things. In the quantum world, the world of the very small, particles aren't points, they're waves, waves of probability. When I say a proton is here, what I really mean is there's a high chance it's here, but there's also a small chance it's over there, and a tiny, ridiculous chance it's way over all of there. It's not in one place. It's smeared out. It's fuzzy. Let me give you an image. Imagine you have a high brick wall and a tennis ball. You throw the ball at the wall. Classical physics says, ball hits wall, ball bounces back. Simple. But in quantum mechanics, the ball isn't solid. It's a wave. And when that wave hits the wall, something strange happens. Most of it bounces back, yes, but the wave doesn't stop abruptly at the surface. The mathematical function describing that wave, the amplitude, penetrates the wall. It fades quickly, gets smaller and smaller the deeper it goes, but it doesn't drop to zero instantly. There's a tail, a little tail of probability that leaks all the way through to the other side, and that means, stay with me here, there's a tiny non-zero chance that when you throw the ball, it will vanish from this side of the wall and appear on the other side. It doesn't break the wall. It doesn't climb over. It doesn't dig a tunnel, it ghosts through. We call this quantum tunneling, and this is how the sun cheats. Back to our protons. Here comes one, racing toward another. It's climbing that electrical hill and running out of gas. Classical physics screams, "Stop! Turn around!" But nature whispers, "Wait," because that proton isn't a point, it's a wave. And that wave function bleeds into the forbidden zone. It overlaps with the other proton most of the time. Almost every time, the proton bounces back. But once in a while, just by sheer probabilistic luck, the proton finds itself on the other side of the barrier. It didn't have the energy to get there. It didn't climb. It didn't cheat in the way you think of cheating. It just was there, and the moment it's there, snap, the strong nuclear force grabs hold. Fusion happens. A gamma ray is born. That gamma ray bounces around inside the sun for 1,000,000 years, slowly working its way out, and eventually escapes as visible light. That light crosses 93 million miles of space and lands on your face. That's it. That's the only reason the sun shines, because protons behave like waves, and waves can be in places they're not supposed to be. But here's the part that'll blow your mind. This almost never happens. The probability of any individual proton tunneling through and fusing, astronomically low. If you were a proton in the sun's core, you'd have to wait, on average, about 59 billion years for it to happen to you. 9 billion years. That's older than the solar system. And this is actually a good thing. If tunneling were easy, the sun wouldn't be a steady lamp, it'd be a bomb. It would burn through all its fuel in seconds and explode. The sun is a terrible nuclear reactor. A cubic meter of the sun's core produces less heat than a cubic meter of compost. Less than your own body, volume for volume. The only reason the sun is bright is because it's huge. There are so many protons that even though the reaction is pathetically slow, the total output is massive. We're alive because of a paradox. The sun is hot enough to warm us only because it's cold enough not to explode. And it's burning at all only because matter isn't solid. Let me take you one layer deeper. When a particle moves from point A to point B, it doesn't just take one path. It takes every possible path. It goes straight. It loops around the moon. It zigs and zags. It goes to the edge of the universe and comes back. Every single route, no matter how absurd. To figure out what actually happens, we add up all those paths. We sum their amplitudes. Think of each amplitude like a little arrow on a clock. As the particle travels, the hand spins. The direction depends on the time it takes. For the crazy paths, where the particle does wild, nonsensical things, the arrows point in random directions. They cancel each other out. They add up to nothing. But for the sensible paths, the arrows align. They reinforce. And that's why a baseball flies in a parabola and not a corkscrew. But here's the magic. When you do this for a proton approaching a barrier, there are valid paths where it penetrates. The arrows for those paths are small, tiny, but they don't cancel completely. There's a residue, a faint little arrow pointing toward fusion. That arrow is sunlight. It tells us something profound. The rules of allowed and forbidden aren't walls. They're slopes of probability. Steep slopes, yes, but not cliffs. When you push a wall, your hand doesn't go through. Why? Because the probability of every atom in your hand tunneling through every atom in the wall at the same time is so insanely small you could wait 1 trillion universe lifetimes and it wouldn't happen. But it's not zero. It's just very, very, very small. In the sun, though, there are octillions of protons. So even though the chance for one is tiny, the chance that some will tunnel, 100%, the sun shines because nature plays the lottery. And with enough tickets, somebody always wins. So what does this mean for you? It means the universe is softer than it looks. It's not a rigid machine made of gears and levers that do the same thing every time. It's a shimmering, vibrating dance of possibilities. Everything you see is the result of a gamble. When you look at the sun, you're looking at the winners of a cosmic lottery, the protons that got lucky, the ones that slipped through the cracks in reality. And think about the light itself. It travels 93 million miles as a photon, a quantum wave. It hits your retina. It triggers a chemical reaction. Electrons jump, signals fire. That reaction is also governed by quantum mechanics. The entire chain, from the birth of light in the core of a star to the moment you perceive it, is a chain of quantum accidents. We used to think science was about predicting exactly what will happen, that if you knew the position and speed of every particle, you could predict the future with certainty. That was Laplace's dream. But we were wrong. Nature is inherently unpredictable at the bottom. We can't say, this proton will fuse at 2 p.m. We can only say, there's a chance. And you might think that's frustrating. You want certainty. You want control. But I think it's beautiful, because if the universe were rigid, if it followed the classical rules perfectly, the sun would be dead. The stars would be cold. The universe would be a dark, silent graveyard of particles bouncing off each other forever. It's only because of this fuzziness, this quantum uncertainty, that energy can be released, that stars can shine, that life can evolve to look up and wonder. We exist because of a rounding error in the laws of physics. We exist because the walls aren't quite solid. So the next time you step outside and feel the sun on your face, don't just think, oh, it's warm. Think about the protons. Think about them racing toward each other billions of years ago, deep in the core of a young star. Think about them slamming into that invisible wall of electrical repulsion, over and over and over. Think about the ones that failed, and then think about the one that didn't, the one that ghosted through, the one that became light. You're touching the quantum world every time you step into the sun. You're bathed in the evidence that reality is stranger, deeper, and far more mysterious than it seems. And honestly, that's the way I like it. Thanks for watching.